version is now planned, and we are fully prepped for the same. So CellStrat has always been a part of Aventus, and the name of the hackathon is Aventus. So thanks once again, CellStrat, and we look forward to these pre-workshops and the hackathon as a whole. Thank you so much.
Thank you, ma'am. Thank you for that introduction. I'm just sharing the hackathon web page. I believe it's hackaventus.com, and you can see this is called Aventus 2.0. Is the second time we are doing this, or Dayanand Sagar College is doing this. So as I said that last year also we collaborated with Professor Vindhya at Dayanand Sagar. It was an exhilarating experience. If you are a student, we do recommend you apply to this hackathon. And I believe there are many teams presenting this from in various domains which you see here. So it seems to be a very exciting hackathon with attractive cash prizes as well, which you can see here. So do apply, and these set of workshops are in order to create thought leadership or training for the hackathon team, and provide them some inputs for some potential product ideas. And I believe they are also inviting their venture arm called Derby Foundation for potential startup investments in that hackathon. And you can of course see CellStrat here, which is our company supporting this program. So we are very pleased to partner with Department of AI/ML at Dayanand Sagar, and we are attempting to train the community with some of these workshops which will help the teams to come up with interesting ideas for hackathon products. So with that, let's get started here. If anybody has
yeah, just a quick question. The prerequisite is that criteria is only students have to take part, or working professionals also can do it, or?
Professor Vindhya, what do you say?
There's no restriction as such. Last time we had only students. However, we can keep it open to professionals as well. It's a welcome. We definitely welcome the professionals as well. Thank you.
So, ma'am, as you can see that the interest is high, and even corporate developers may be interested to participate.
Absolutely, we welcome them on board.
Okay, that sounds great. Any other questions, folks, before we hand over to our presenter for today?
One more point, other than Derby, a couple of other investors also have shown interest in the hackathon, so they will be around on those days, and they will be sponsoring the seed money for the best innovation on the spot there.
That's absolutely fantastic, and that can increase the motivation for the participant teams to do remarkable work. It would be a pleasure to see some startups launch out of this kind of event.
True, sir. Let's hope for the best.
Okay, great. So I have one of our top NLP scientists, Poulami Sarkar, presenting this workshop today. So if there are students and working professionals here, you can take some ideas, and hopefully that can help you in your hackathon entries as well, or your larger AI journey, also. So Poulami, are you ready?
Yeah, sure. Let me share my screen.
Yeah.
Is it visible?
Yes. So the recording is on. So Poulami, over to you. All the best.
Sure. So I would start with a very short introduction about myself. I am in the analytics space since back in 2015. And before that, I have worked as a developer. So my total experience is more than 12 years. And as of now, I'm working very closely with LLMs. And even in my current role, which is of a lead data scientist, I do develop a lot of applications, POCs for my current companies using different types of LLMs. My keen interest is to explore different architectures. And today, again, we would be talking about something very core to the LLMs, that is the architecture. I know the hackathon is all about building the apps, but Before that, we need to build a very solid foundation on what these LLMs are actually based upon. That is the architectures of different models. So transformers, as we are all very, very aware about transformers, I know all the webinars till now have spoken about transformers. Mamba is something very new. And today we will dig deep into that. So to start with, for the agenda, I would be talking about the architectures a little bit, architectures of transformers, and also the drawbacks and the need of getting into something like Mamba. And so basically what Mamba is something called state space models. So we will have an overview of the state space model. Then we will move into why there was a motivation of improving those state space models and creating something called Mamba. It's a weird name, right? Mamba is a weird name, and we will also discuss why the name is like that. Besides that, we will also do a quick performance comparisons just to understand how the architecture has really helped. And I also do have an inference notebook at the end. I will be sharing the link to my GitHub. You could actually look into that and take in some of those codes and maybe try out some on your own, right? So digging right into it, right? Transformers, we are extremely familiar with the transformer architecture. To understand how it is different and how transformers and state space models work, let's start with the very basic sequence model, right? So what exactly are sequence models? Sequence models are when you have a sequence of tokens and you are given the task of predicting the next token in the sequence. So that is what the main idea of a sequence model is, to predict the next token. So let's say here I have the
Yeah, I
right
think
hand side.
Poulami, the slide is still on title slide.
Okay.
Maybe you want to share the entire screen, not just the PPT.
Let
Yeah,
me
now,
do that. Let me do that.
yeah.
Yeah. Give me 1 second. Entire screen. Is it visible?
Yeah, we see transformer slide. You can put it in presentation mode. Yeah, it is visible.
Right.
Yeah. Okay.
Okay. So on the right hand side of the screen, what you're seeing is basically the familiar architecture diagram of the transformer. However, today I will keep it very, very simple because this presentation, this webinar is going to be very, very tech driven. So there is a lot of equations are there, a lot of different terminologies are there. So I'm trying to keep it very, very simple. So let's say I have a token 1 and I have a token 2. So in a sequence model, be it any kind of sequence model, be it a transformer, be it any LSTM or even RNN, the idea is prediction of the next token. So I have a sequence of tokens represented as colors. The attention model in layman's term is going to work by looking at the relationship between these tokens that come before the one which is to be predicted. So we have to then calculate the attention math. So without getting into too much nitty-gritties of how the math is calculated, I'm sure everybody is aware about it. So without getting into that, we are basically going to calculate the attention between the tokens just to understand what would be the prediction for token number 3. Now, this sequence of transformers, as and when your number of tokens increases, what happens is very, very naturally, your calculations will also increase. So let's say if I have 3 tokens, I have to predict the 4th one. I have to calculate the attention between token number 3 and token number 2, token number 3 and token number 1. Why? I also have the attention calculations between token number 1 and 2 and 2 and 3 in my cache or buffer. So it is a combination of all those attention scores that I'm having across the sequence. Now imagine if this keeps on getting longer and longer, which the situation is as of now, as of today. We generally get tasks of, predictions or summarizations or any kind of LLM tasks. They work on very, very long sequences. So what would happen? We'll keep on increasing the number of calculations. So when I say calculations in loose terms, it is basically all the matrix multiplication that has to happen to calculate the query, the key, and everything that is needed for your attention model. So you can see as farther we can get into it, the more number of calculations you are going to make, and that is going to make your solution computationally extremely expensive. So now what is going to help us? So let's say state space model. State space model is something which is a different school of thought. Basically, it's not going to look into all the tokens. What we will do is that in a state space model, the way it works is by having a little piece of storage, this green color space. For example, this is the little piece of storage we are thinking about. This is called a state space. Now, what is going to happen is that you think of this state space as a vector. Now we take one token, we pass it through some kind of function here. So this black straight line, this here, there would be some kind of a function here, which would actually compress your input and it would store it here in your vector, in your state space vector. So we will discuss in the upcoming slides about the function that is going to compress it and how the whole thing works out. But for simplicity, let's just keep it at a very, very high level as of now to understand the difference. So let's say the second token comes in, right? Now what happens is the second token also goes through a similar kind of function. It then gets compressed. It then gets stored in the state space. So we are updating the state space. Now one thing to notice here is, unlike transformers, we are not keeping the token 1 into our memory. So we have gotten rid of token 1. Now we just have token 2. And we have taken the token, we have transformed it, we have done some kind of compression, and then we have stored it in the state space. And then we get rid of the token 2. In comes token 3. We do the same thing with token 3, compress it, store it in the state space, right? So basically what this is doing is it is getting rid of all those additional computations at each step that we were doing for the transformer model. So the crux of the matter is basically, if you look at it side by side, is you have a transformer model. For this, you have to store all the tokens x1, x2, x3, whatever number of tokens there are, you have to store it. In case of state space model, you don't have to store all the tokens. You just have to have a state space. Now the question is, the state space that we are talking about and the long lengthy sequences that we are talking about, the space consumption of the state space is going to be huge, because let's imagine a token length, the input token size of millions or even thousands, right? So we are compressing everything, we are storing in a matrix, the size of the matrix keeps growing, right? So then is it more computationally expensive to keep on computing more and more matrix multiplications, or is it going to be more expensive to create a huge storage matrix, right? This is a trade-off. Now what to choose depends upon what your problem is. Now let's say if you have a token size, the sequence size of a certain length. Yeah, somebody's asking something.
When you are saying it, what do you mean by expensive, and how do we decide that?
Definitely, that's a very good question, and the answer to your question will actually come up in the later slides. We will also talk about the architecture of the GPU, and there you will see the time taken and the computation speed and all those things we will get into. When I say expensive, just imagine the amount of computations that are going to happen. So in case of transformers, the number of computations are exponential, right? So if you have 4 tokens, you're going to compute the attention between each of those tokens along with the attention of token number 4 with all the other previous tokens, the number of computations. However, when it comes to SSMs, at every step, you just have to do one calculation, that is compute the compression and store it in the state space. Does that answer your question?
Yeah.
So I got another question. Like, where are you going to have your state space? You say it's not the RAM, it's not the memory. So you're going to put it in somewhere in the solid state drive, somewhere in the hard drive, you mean?
No, it is going to be in your memory. But if you think about it, the storage for all the sequence tokens. So let's say if you have, for example, 20,000 tokens in your sequence, in case of a transformer, every step, as I was showing you before, for every step, you need to access the previous tokens, or you need to cache the attention scores in between those tokens. You need to store many interactions. But in case of state space, you just have one matrix in place, and that is what you store in your memory. It is going to be still the GPU memory, but the storage that was there for transformer was for all the tokens, plus there was computation at each step. Here, the storage is only in one vector, n by n vector, and the computation is happening only once. So you compress each token and store it. That's it. No attention calculation is happening.
Thank you.
Mm-hmm. Any other questions? Fine. So it depends on your sequence length. Let's say if you have a sequence length of, and I also have a slide at the end on performance on it. So let's say if you have a sequence length of 10 to the power 3 or 10 to the power 4, the transformers are still a better option because looking at their accuracies, they still do a better job. Not really better than SSMs, but at par. But when it comes to huge sequence length, let's say 10 to the power 6 as sequence length, it is much easier in terms of number of calculations, in terms of time taken to do an inference. It is a lot better when we use a state space model if your sequence is very long. And we will see why the reasons are and what the nitty-gritties are.
Poulami, yeah.
Yes.
There was a small question. So the hidden state is linear in calculation, right?
Right. Yes.
Okay.
So we'll get into the math in a while. So before
Okay.
that, let's see if we all are in the same page right now. Till now, if there is any confusion on this. Right. So okay, fine. Let's get into the math. The linear piece that one of you is talking about. Sorry, I can't see the list of participants, so I won't know the names. So basic calculations. I told you that there is a state space. I told you that it gets updated. So the question of the hour is, how do we define the state space? We will talk about how do we update it. And more importantly, if we have an input X, how do we get the output of it, right? So these are all the questions that are there. So if all of you might have gone through gradient descent algorithm, right? The very basic of ML is the gradient descent. So at each stage, the training happens. Incrementally, we train the model to become more and more close to what the actual predictions are, right? So here also in state space models, we start with a bunch of data, like any other ML models. We start with a bunch of data, we train on that. And then this is what I'm talking about in the perspective of training. So as of now, we have the trained state space models in place. We have already, like we have it in the Hugging Face and you can actually use it. But when it comes to actual training, how does that happen? You have a bunch of data and then you have to train your model on the data so that it can do a proper inference. Now for that, the main part of it is basically you're updating the state space, right? So you start with a state space. The starting of the state space, as in any kind of machine learning model, it starts with the initial weightages, right? So there are many different ways to initialize the first state. I will not get into all those because that is a different conversation altogether, right? But we will talk about how do we update the state space. So basically, the state space has to depend on two things: the old state of it and the current input. So this is the first equation that you're seeing in the start. This is your delta H. Delta H depends on two things: your H, which was in the previous step, and your X. X is your current input. Now, they have to somehow, the state space models, people who were making it, they have to somehow create a very simple relationship. And when we talk about simple relationships, linear relationship is the one which comes in mind. So your delta H is basically a linear relationship between these two variables. Your A and B are just coefficient matrices, which are trainable. We will talk about how we train them and what they are about in a bit. Right. However, in the second equation, you still have one piece of it missing. That is the small delta, which is the growth rate, right? The train rate. This gives you control on how much you are going to tune your linear relationship, step size. So step size is very, very familiar when it comes to ML models. So basically, it's nothing but, and mind you, we are talking about vanilla state space model. It's still not Mamba yet. So vanilla state space models, we are establishing the relationship between the X and the previous state, and we are trying to calculate the new state. So delta H is nothing but the step size multiplied by the relationship, linear relationship. And once you have the delta H, what we are going to do is simply, we are going to add it to the previous H1. And that is how we get the H2, right? This is the new state. Now, once you have the new state, it is then easier. So I think most of you who would have done LSTM or GRU, you would be, these equations must be looking very, very familiar. So there is a hidden state, and what we do is to calculate the output of it, we are going to multiply the hidden state with the input, and X2 is your output there. And again, we will get into C and why, what we can do with C and what is it about. So basically, your parameters of A and B and also C, I have missed writing C here, but also C, these are all trainable parameters when it comes to state space models. And we will have to, initially at the very beginning when we start the training, we create the states, the H matrices for all the inputs. So you have a static situation where then what happens while inference, you just get an input, pass it through the state, get an output. So there are no extra computations like transformers where you are trying to understand the relationship between each of those tokens and the dependencies. So you're getting rid of all those things. And there are pros and cons of it, which we will talk about. So before that, any questions on this?
Yeah, it seems a bit like RNN LSTM, right? So RNN equation was similar, right?
Exactly. Yes.
But Poulami, the issue in RNN was in case of long sequences, it was hard to maintain, previous memory, right? So that's what we attempted to solve with positional embedding and parallelization architecture. So is Mamba able to solve all this as well?
Yeah. So you see the main difference, sorry. Give me a second. So the main difference when you think about RNN or LSTM versus state space models is that you never had something like this, the matrix, the state matrix, where you are actually collecting all those tokens and compressing it and storing it in one space. When it comes to LSTM, when it comes to RNN, you are doing it real time, right? You are taking each of it, you were doing the computation and you were then throwing out the input, the output, and then you are moving on to the next. But
Right,
here what
right.
you have is you have certain amount of context in space. Although
Hmm.
they are compressed, Mamba is all about compression. So you have compressed it and you have stored it. So information loss is not happening here as compared to RNN or LSTM.
Right, correct.
Yeah, I have two questions.
Mhm.
One is, are the A and B single numbers? Single numbers that are trainable? Because
Single,
you have written it
single
scales
numbers.
the inputs.
Uh-huh.
Are those single numbers? Only one number that are trainable?
No. These are all matrices. So when it comes to training ML models, you will rarely get a single coefficient. It's not a line, right? It's not one dimensional.
Yes, I
So,
understand that.
mhm,
My main question was, if
mhm,
A and B are weight matrices, then
mhm.
that has to be A and B are linear transformations of H and X. It does not scale, right? Because scaling is something if you multiply it with a single number, that is what scaling means. So I had a confusion on that one. So I think it should be linearly transforms the H and X, right,
I'll get
into
to
a
that.
smaller
I'll get
space
to
or
that.
anything.
Yes,
Yeah.
yes, you're correct.
And
So
the
see,
other
this
thing,
is state space model. Just give me one moment. So
sure.
this is a vanilla state space model. But when it comes
Yeah.
to Mamba, obviously there
Mhm.
has to be something different, right? If you see this
Yeah.
looks very simple, right? You're giving same weightage to all the tokens. From what it looks like, right? Even if it is a matrix, you're training the matrix, you're giving same weightage to all the tokens. So then how do we know if a certain token is very important? How do we know that, right? So that is something, the linear dependency that you're talking about. I will get into that just in a moment. But before that, let's hear your next question.
Okay, yeah. So the delta, is it a new hyperparameter that we have to take care of maintaining this?
Yes. So delta itself is again a trainable parameter. Here it is a step size. It is, if you have done a gradient descent, there
Mhm.
what delta is step sizes, it is very, very similar to that.
Okay, so it's not it's trainable in the model itself, right? We don't have to tune that.
Yeah, no, you don't have to train it while you are inferencing. This part
No,
is
not
what
while
I
training.
yes, while
So I
training you have
was
to train.
you have to tune that manually, or does the model learn the delta thing while training? Yeah. So that is what I was asking. Is it
Yes.
similar to a learning rate that we have to set, or does the model learn the delta thing?
You have to initialize it, and the initializations might have, there are algorithms for initializations, right? So you can initialize it, but when you first of all, you don't really train it from scratch like we do it for what do I say, neural networks or RNN or something. We don't train it. There already are trained models like transformers. There are trained models, right? So you can actually tune that model. You can take that model out, you can tune that model. So this step size parameter, there you can play around with it. In case your data is not fitting well, you can play around with it. Yeah.
Okay, so that is something that we have to set, right? That is not the model learns. Okay, yeah.
It
I
learns.
have
So
one question.
the out of the box model that you get from Hugging Face, I will also show you those. So the out of the box models that you get there, they would already have everything set, right? Just like you can take it out and tune it. It is very similar. You can then, you don't have to start from scratch. That is all I'm saying. So you can take that model out and then you can, just like you use LoRa or something to retune your model, you can use those things here as well.
So one last question: is the C the scaling thing in X2 in the output of X? Is C what a single number that scales
No,
X2
these
and
are all
X1?
matrices. No, C
These
is
are all
also a
matrices.
matrix.
Okay.
Right? Okay.
I have
Any
just
more
one
questions?
question.
Go ahead. Yeah.
Yes, I have just one question. I was not able to follow the new state calculated equation. The H1 and H2. Is it like the new H1 is the old and H2 is the new state that has been calculated, and from where we are getting these values, especially H1?
H2 is the new state. So I understand the confusion because I have been using H in the previous equations. But H1, let's say in your previous step, the state that you had, let's say this state, right? This state is H1. This is H2. Okay. So in between, there was a delta calculation happened, right? So when I took you through the initial stages, I told you that the next token will come in, you will compress it, you will store it in the state space, right? Now, it is not encryption algorithm, right? I'm not going to take that token and create an encryption, do an encryption function on it and just store it in a matrix. That is not going to happen. What is going to happen is we are going to update the state. And the equation that I'm showing you here is that how are we going to update the state? The state has to depend on two things: the new X that is coming in and the previous H that was there, previous state which was there.
Okay. Okay.
Yeah, this is sequential modeling. So H always represents the hidden state of the model at the moment, right? So at current time step, what is the hidden state? That's what H means. So you have to always calculate H2 for a previous H1 for the next time step. It's a sequence modeling process.
Thank you. Thank you.
Anyone else have questions? Okay, let's move on. So this is the basic calculation of what state space models are. Now Mamba is actually adding one more word to the state space models. The word is selective. So the name Mamba, it actually comes from the presence of so many S's. So it's a selective structured state space model, right? And then that sa sound that we are having, that is compared to the hiss of a snake. And that is why it is called Mamba. So what was the motivation to actually modify this into something else, right? Selective, the word selective, we got it. So this is very closely tied to the questions that we are having in the previous slide, where the question was basically if this A and B and C, these are trainable or not, and these are linearly dependent on something or not, these questions, right? So what they have found out, the researchers, is that there are two particular tasks where the state space model, the vanilla state space model that we saw till now, that was not really effective. The first of those was basically selective copying. So selective copying is an example. Think about a task where there is a comment on Twitter. I've taken the example of Twitter, but just think about any application. You have a comment and you have some bad words in the comment, right? Some abuses, some harmful words. And your model, you're asking the model to remove all those bad words and do it. So like LLM models, like any other LLM models like Llama or Mistral or Gemini, if we put in that prompt and then we ask it to block the harmful tokens, it will basically give you back the like better comment, right, with removal of all those words. So that is called selective copying. Why? Because you're copying certain tokens and you are leaving away certain tokens. So in case of state space model, the problem is, as somebody was asking me before, the kind of weightage that we are putting on each token, they seem to be very, very uniform, right? There is no, because if A and B are matrices, there is just very less scope for us to give more weightage or less weightage to any kind of token. So let's say for bad words, if I'm trying to keep less weightage compared to good word, then that scope is not here. It is not, if I talk in a language model perspective, state space models are not content aware. It is context aware, but it is not content aware. So it will not know if a certain part of my sequence is more harmful compared to another part of the sequence, right? But it will know that they are connected. Another thing is induction heads. So let's say if I tell you that whenever I'm going to see a black token, just giving a very layman's example. So you see a sequence here of colors, right? So whenever I see a black token, the next one will always be blue, and whenever I see a blue token, the next one will always be black. Let's say this is the reasoning. Now here, this is called induction heads. So here, not Mamba, state space models, they don't have this capability to decipher that, okay, I have to remember that this was the black token. And whenever I see this again, my reasoning will be content aware. Whenever I'll see a particular content, I will then give another of those contents that I saw before. I will spit that out as the next one. So you cannot really teach a state space model that, because there is no way to select. There is no way to give preference to certain things. So because now if you compare this to a transformer-based model, right? So transformer-based models are better at this. Why? Because you have attention scores between all those. You have the relationships between each of those tokens. And also in the grand scheme of things, you also have the relationship of the one which is the latest token with all the other tokens that preceded it. So transformers are better at doing these two things. However, they lack when the context length is huge. It's very big. So that was the motivation to actually introduce selection property into the state space model. And we will talk about how that happens. So here is where the linear equation comes in. As you can see here, the B and the C, right? Those are not really a single matrix or a vector. They are also linearly dependent on, again, the two things, the input and the previous state. So what is the use of making these dependent on the previous state, right? So when you're actually making these dependent on the previous context, it is capturing the content response to the next token. So let's say if A was, or B, let's say B, if B was a static matrix, in that case, the weightage that you're going to give to each of these tokens are going to be same across your sequence. However, if you make it linear, a linear dependence on the previous token, it is going to capture some amount of information saying that, okay, if I see a blue token, the next one is black, which means there is a connection between these two. And it is trained in that way to understand that connection, right? So here we are just trying to capture the connection between the previous token and the next token. Something very similar to what attention model does, creating an attention. However, when the attention model does that, it has to go through multiple number of other calculations, many matrix multiplications. Here you see it's a very simple linear relationship that we are trying to establish. Any questions on this?
I mean, frankly, the right equations are woozy for me. So I don't understand the right equations.
Yes, it is easy for Poulami, I had one question. So x1 is the input from the last step, right?
Yes.
And we are calculating x2 based on taking into account the x1 as well. So that is what is new, I mean, in this selective thing.
Yes. So it is hazy because I have taken it up from the real paper, the PDF. I've taken a snapshot of it. I have not really written it down in the PPT by myself. Apologies for that. But what we are trying to establish through the linear function of input is that whenever we are compressing the token, I told you we are compressing the tokens. So whenever we are compressing the token, it is linearly dependent on the content of the token itself and also the previous state of it, previous state of your algorithm, H1. So it is not without context. It is about the word, about the previous state as well.
Hi, Poulami. I have a question. When you put the delta with the brackets x1, it means that delta is a function. I mean, x1 delta is a function of x1, right? Like
Delta is a function of x1. Correct. That is true.
Right. And b is also a function of x1. So which is the
Yes.
previous state? Why is there
Previous state is h1.
x1?
H1.
Yeah, h1.
Yes.
Sorry, but what x1? Why isn't there? Why isn't a dependent on x? Like why? What is the relation? Why is that?
Yes.
Yeah. Why
Yes.
is it?
That is going to be covered in the next lines. If you can read the next lines, then great. Otherwise, I'll take you through what a is. And a, as you see, it's not a function of anything, right? It is just we are multiplying
Independent
h1.
parameter, right?
Yeah. So
Yeah.
how do we calculate a? And a is a whole different story. But before that, let's talk about b and c and delta. Those all are going to be functions of input, right? So if you have any questions on these, then I will address. Otherwise, we will go into what a is.
Poulami, by any chance, this delta is not the Dirac delta, is it? Yeah, it's not that, right?
Sorry, come again. I missed your question.
Is it not the Dirac delta, Dirac delta function that we have 0 or 1? Is that's not it, right? This is something else.
No. This is your step size first of all, but then step size is also not a discrete step size, if I may. So it is going to be a function of x1, especially when it comes to Mamba. In vanilla state space model, if you see, it's not a function of anything.
Okay.
This is still discrete, but here it is not discrete. Here it is dependent on your token. So which means if your token has a word like, let's say dog is your token, right? So your step size will depend on the content of your token. If it is cat, it is something else. If it is dog, it is something else. It is trainable.
Okay.
And delta is always linear, or it can be trigonometric or any other
Delta
kind
is
of
linear.
function.
Delta, b and c, these are all linear functions. A, however, is not linear.
Okay, thank you.
Yeah, I'm getting a sense of it. Basically, we are replacing trainable linear parameters a and b with, making a and b functional themselves. So that it is not having constant a and b state after time step after time step. The a and b values themselves become variable based on which time step you are on and which x1 you are on. So that's why delta of x1 makes it parameterized based on x1 instead of having a static a and b. Because in the previous slide, she stated that the problem with state space model would have been the a and b would have been constant across time steps. But now with this equation, the a and b themselves have become function of where they are in the process. Function of x1 basically. And if you go to the next slide, you have stated that the problem was not the one before. So the slide before, here you have stated that the problem of plain state space model is that A, B, C, D are same for every token on the left bottom. But you want to make them a function of where you are currently. So cat and dog would be treated differently, and they would influence the parameterized values of A, B, C, D.
So think about this. Unless you treat the tokens differently, you will not be able to handle problems like selective copying or induction head.
Yeah.
And in case of transformers, this is not a problem because you anyhow are capturing, you're doing thousands of attention calculations and you're capturing the relationship between these tokens. Now the drawback, if you think about it in a transformer, the black and the blue token, the attention between those two, those will not only depend by the attention score between black and blue tokens, that will also be dependent on where they appear in your sequence, right? So it is multiple attention scores that are to be taken into consideration. However, in state space models, you are getting rid of those many attention scores and those many relationships. You are just making it dependent on the token itself.
So, okay, yeah, cool. That's okay. I got it now. Okay, thank you.
Yes. Now the next burning question is, what about A, right? So A is still not a linear equation. A is a little complex, and I am going to try to cover it as much as possible to give you an idea at least what is going on. But it is very, very intensive in equations and everything, right? So A is a matrix. A, what it does is it captures the context. It captures the information from the previous states, previous all states, right? So if you're, let's say, at the 100th character, A is something which will keep on collecting the informations from each different states. So that is why it is actually multiplied with the state space variable h there. So it is collecting some amount of information, and it is keeping the context, so to say. Now, this is actually, if you think about it, this is actually the core of any language model, to keep the context in mind, and that too without doing a lot of matrix multiplications. So I am not against matrix multiplication, but I'll tell you why they are going to affect your model's training and performance as well in a bit. So before that, A, right? So A has to be very, very correct in capturing all the informations that was there till now in the sequence. And to calculate A, there is something called a hippo theory, which I will talk about in the upcoming slides, right? So before that, Fourier intuitions, right? Most of us would have done Fourier series in college, and how it works is basically it decomposes a signal, as we all know, into sinusoidal functions, and when we add up all those sinusoidal functions, that is where we can recreate your original signal. Now, hippo is a very, very similar technique, but instead of sinusoidal functions, it uses something called legendary polynomials. So we will not get too deep into what legendary polynomials are, because that is not the scope of today's discussion. Just to give you a very, very rough overview of what this is basically hippo is one technique which we use to capture the sequence till now. So A, the main part of the main function of A is to capture the context. How we do it is we create a matrix. How we create a matrix is through a function called hippo, where till now whatever has been there in your signal, that is captured through something called legendary polynomials. Now, if you have to understand it in a very, very layman's term, look at this, the red one, the red signal that you're seeing here. This, let's say this is your original signal, right? Now, when you are going to apply hippo transformation to it, here you see it has recreated it, reconstructed your original one using hippo. However, you see it's not as accurate, right? It's not accurate here, but it's accurate here. So the speciality of hippo is that it is good at approximating the signal and giving more weightage to very, very recent patterns. So the recent patterns which are here, that are replicated better compared to these. And this is intentionally chosen so that we can give more weightage to something which is like nearer in your sequence compared to which is way back. Imagine a book, right? So a 500 pages book. You need to give more weightage to the prior pages compared to the first page, right? So this is what hippo theory is about, and this is how we actually address capturing the context using the matrix A. So matrix A is basically at each step, matrix A is going on capturing little bit of the context so that the whole context of the signal will be fine at there is link to the XIF paper on Hippo. You can actually get in there and try to look at all the calculations. I would not be able to, cover everything, but overall, this is how it captures your context. So any questions on this?
So we are giving emphasis to recent signal compared to older signal. So that's what this achieves.
Yes, and we are doing all this. Why? Because we need to keep the context alive. Even if your sequence keeps on getting longer and longer, the context had to stay alive. And like Vivek, you were asking this question before, that how is it different from LSTM or RNN, where vanishing gradient happens, right? Here, we are trying to take all these steps so that we are not missing out or losing any information.
Got it.
Right. So here is everything in a class, right? This is the scarier version of what I have covered till now. We have SSMs, which are state space models. We call it S4. And when we add S selection to it, it becomes S6 to it. So all these equations that are here, they are all discussed till now. And don't be scared with all those B, D, and L. It's basically your batch size, sequence length, size of your vector, all those things. So it is a very formal way to represent this. However, we are still not done with the Mamba architecture because we have not spoken about how it helps longer sequences. We have established the fact that transformers does a lot of calculations and it takes time and number of calculations are more. But how does Mamba help? So I would like everyone to concentrate on this word here, scan. So we will talk about this in detail in the next couple of slides. So architecture of Mamba, right? So to take care of longer sequences, and this is again an extract from the Mamba paper, there are three classical techniques that the Mamba architecture uses. The first is kernel fusion, the second is parallel scan, and the third is recomputation. And we will go through all of those. But before that, let's talk about the GPUs. So in the beginning of the presentation, I remember we were addressing these questions, that what is happening, where are we storing, why is it slow, all these questions, right? So GPU, we have this image of GPUs in mind, that it is a huge storage space and it is very, very fast. And that is all true, right? That is all true. So there is just one problem though with GPUs. So GPUs, there are two sections to your GPUs. There is DRAMs and there is SRAMs, right? So SRAMs, if you see, SRAMs are very small compared to what DRAMs are. The numbers that you see for GPUs, the GBs, numbers in GBs that you see when you try to look at GPUs, those are basically describing your DRAM size. But SRAMs are very slow. What happens is, let's say if you want to do a matrix multiplication, it will first copy your tensors or matrices into SRAM. Then your GPU core is basically going to access your tensor or matrix from SRAM. It will quickly do the calculation and then it will copy it back to the DRAM, the actual memory. Now the problem is, calculation speed is very fast when it comes to GPU, and you'll see the numbers on the right hand side. I don't know how much it is visible, but I think once Vivek shares the slides, you'll be able to go through it better. So the calculation speed is not a problem. It's very fast. The problem is copy pasting. So copy pasting huge tensors from DRAM to SRAM and then doing the calculation speedily, and then again copy pasting it back to the actual memory, right? Now imagine transformers. So many matrix multiplications, essentially they're all matrix multiplications, right? Huge tensors, matrix multiplications. When you do that, that many times, what will happen is quickly your operation will get done, but then you'll have to wait in queue to get it copied into the DRAM piece. So that is taking time here, right? So it is not the number of computations that you're doing. It is moving around the IO operations that is going to take you time. And this is exactly where Mamba architecture is going to help. So first of all, I asked you to concentrate on the word scan, right? Scan operation. So there is a very, this is a very, very common problem. Anybody who would have worked or would have tried competitive programming, you would know about a problem called prefix summation, right? Prefix sum array. So in that problem, what happens is that you're given an array and then you have to calculate the sum, right? Calculate the sum. So for example, 9, 6, 7, 10, 8, and then 7. So you have to sequentially keep on adding them up. So 9 plus 6, then 6 plus 9 plus 6 plus 7, 9 plus 6 plus 7 plus 10, then that plus 8 and that plus 7. You have to do it sequentially. You have to scan through each of those numbers and then keep on adding those, right? So this is a basic scan operation. Now, if you think about it, SSMs, be it vanilla SSMs, be it your Mamba, whatever it is, you have to calculate the states here, the hidden states, H. So here also, again, the same thing is happening. You're doing the scan operation. Be like leaving aside all the complexities, all the linear and whatever we talked about, all those age calculations that we are trying to do. Every time, unless you know the x1, you won't be able to calculate h1 because h1 is dependent on x1. So this is a parallel. This is going to be a scan, right? Sequential scan, not parallel. Now this is going to take time. One way to look at it is, what if this could be parallelized instead of doing it sequentially? So there comes parallel scan, which Mamba uses. So here there is a very, very naive representation of how you can use parallel scan. So instead of waiting for the next token, let's say if I'm waiting for this token, right? I still have these two in my mind. I have these two in my memory. So why not create sum of these and then add this sum to the next step, right? Create a sum of these and then add this sum to the next. So this is how it's not a proper parallelization. It's not like you are treating each of those numbers separately, but you are still spawning multiple threads to do a binary operation in parallel. So you're also having a synchronization step in between, but you are still not waiting for all the inputs in the sequence to get added until you can complete the whole operation. It is making your calculations a little faster. So how much faster? It is order of n if you don't do it in a parallel way. It is order of n by t, t being the number of parallel threads that you spawned. So it actually is going to speed up your process a little bit. So that is one part of it. The second thing that Mamba uses is very, very close. So kernel fusion is something which is which addresses that problem. So here what happens is they do not really wait. So basically think of this. You load the input, compute the operation, and then you save it back to the DRAM. And then again, you load the previous result, and then compute the second operation, and then you save it back. Load the latest result, compute the operation, save it back. So you are doing a lot of IO operations. So instead of saving it back so many times, what Mamba does is, they call it kernel fusion. They are basically doing all the operations sequentially. So make the operation sequence faster they call it fusing the kernels, but in layman's term, what is happening is one after the other, those calculations are happening. You're not copy pasting multiple times. So this also speeds up your operations. So the main bottleneck, if you think in the Mamba architecture, was basically creating those intermediate hidden steps, H1, H2, H3, H4. Once you are done with those, you are done for the day, right? You are just going to pass your inputs to those H1, H2, H3s, and you will get the outputs. The main trick is to speeden up the calculations there. And then finally, retraining, right? This is something which I think most of us will relate to. Here, even when we try to train a normal deep learning model, what happens is when we perform back propagation, let's say gradient calculation at each node you have to do, right? So you need to cache the output from the forward step so that you can actually adjust it when you're doing back propagation. So what Mamba does is it doesn't cache those values, it recalculates. And as I said, calculation speed is not the problem. Problem is copy pasting. So since you're not caching it, caching meaning again you'll have to like paste it somewhere, read it from there. So we are not doing all this. We are just going to recalculate everything, and then it is going to save you time. So they have proven that it is actually faster than faster to recompute it during the back propagation. I have not really had the GPU or the system or anything to try it at my end, but I will trust them on their research paper. There is also a snapshot of the research paper. You can dig into the Mamba architecture research paper to get to know it better. So these are the architecture nitty-gritties. This is a very rough picture of the architecture which I have built. Like I have drawn it on hand, so it's not really that great to look at. But the one on the right side, that is taken from the Mamba paper. So here, what is happening is you have the first layer is a linear layer, right? The linear layer is your embedding. You get your data into the D model is basically nothing but your embedded data, the tokens, right? And D inner is basically your first state, the initial state of it. So once you have that, you then pass it through a convolutional layer. And mind you, this is not just one single pass. Like transformers, SSMs or Mambas, they are also stacked layers of many stacked layers. You see there is NX I have written here. So N layers of SSMs or Mamba is going on, which will again capture different aspects of it, right? Just like transformers does, it will capture different aspects of a huge sequence. So you have a convolution layer there so that there is some kind of dependency between those layers, right? So that you capture what is unique about this particular layer. So when it comes to language, the different dimensions, if I think of in a language, could be the grammar of the language, the tone, the sentiments, things like that, right? So there is a convolutional layer. After that is the SSM. The SSM is everything that we talked about till now. After that, your element-wise product would happen. There is an activation function to introduce non-linearity in it, and these particular items, they are very common in all the architectures that you see. If you see Mistral, Llama, anyone, you'll get to see these components. So at the end of it, it is again going through a linear layer so that it transforms back to the original dimension. So let's say your embedding is 512, then the linear layer will again transform it back there. So this is how it works. And mind you, it's not just one pass. There are multiple layers. There are interactions between multiple layers, just like any other large language models. And it is very difficult to show it in one session how those multiple layers are interacting in between themselves, but I'm sure everybody can relate if you know about transformers. So this is the overall level architecture. Yeah.
I had a very small question. Can we think of at the other thing in the Mamba, the thing that's branching out? Can we think of at it has the residual connection, something sort of that we use in transformers. But since there is an activation function as well, so it's
This
somewhat
part,
different.
right?
Yeah,
Yes.
that part.
So yes. I think, see, you can think of it like that, but then it's not really a transformer mechanism because again, if you get into that trap of calculating attentions, right? And then again, that copy pasting and doing all those matrix multiplication, that will complicate your process. Here, what is happening is they are creating the initial hidden state here, right? And then they are updating the state, and then they are basically, your SSM happens here, right? And then this is the first ever copy of your hidden state. They are passing it through a function. They are doing a matrix multiplication here, right? Element wise product, just to approximate it. At the end of it, they are approximating the output. And also the output, if you see output of any language model, it has to, at the end of it, go through a softmax, because there has to be a choice of tokens, right? There will be probability scores of different tokens, and the final one will be chosen. The one with the highest probabilities will get chosen. So there has to be a softmax at the end of it. So there is this extra processing they have in the paper wherein they are approximating the outputs. So it's not really transformer architecture's component.
Yeah, I'm not talking about the transformer architecture. I was specifically talking about the skip connection,
But,
the residual thing
kind of trying to
that
capture.
goes around. Right? It's basically used in almost every model today. So
Yeah.
is that something that? But the skip connection in these models do not have the non-linear activation, if I'm not wrong. So yeah, it is somewhat different. Okay. Yeah.
Right. So coming to the performance, right? After all this, what happened was, if you look at the chart on the right, Mamba's performance when it comes to induction head extrapolation, it's, if you see 10 to the power 6 is your test sequence length, even there it is doing really great compared to the multi-headed attention. Multi-headed attention, the accuracies would drop around this area, which is at 10 to the power 3, 10 to the power 4-ish. So they're actually better when it comes to longer sequences. And selective copying, again, selective copying was a problem with the S4 model, which is the vanilla SSM. You see it's 97 here, whereas compared to that in Mamba, you have around 99.8, which is really great. So it has successfully addressed both of the issues, and it is also doing better than transformers when it comes to longer sequences. So one last thing of it is about scaling, because there are, again, the edge, the hidden state, which we are updating at every timestamp. This is going to be that is going to be huge, right? So that can be a bottleneck. But then Mamba scales better than all the other attention tree models. So when I look at other attention tree models, which are other SSM models, it is better. It is better to scale. Even when we compare it with a very strong transformer model, the Transformer++ is the latest transformer model. Even there, if you look at this orange line is the transformer model, and this one is Mamba. So it is actually not as bad if you look at it. So this is perplexity versus flops. Flops is how you measure your memories consumptions. So the perplexity there is lesser here compared to what we have for transformers. So scaling wise, it's not that bad. It's also doing good for long sequences.
Do you find any LLMs being launched with this? Or all LLMs are still transformer based?
We do have, so in the Hugging Face, the next thing I'm going to show you is basically we do have 2 Mamba models which are available in Hugging Face. That is actually a very good segue to what I was going to show you next. So there's this model, Mamba 2.8, Slim Pajamas is the dataset name here. So this model is not chat fine-tuned. However, this could be used. I have a notebook also here where I have tried to explore it a bit, trying to do an inference from it. T4 could be used here if you try to like replicate it. And here is the configuration of this model.
You can increase the font size a bit.
Let me try to do that.
In the PC control, yeah, this is good. Yeah, it's to the left. It's being cut off here. Yeah.
Yes. So this is the configuration of your Mamba model. Okay. So if you see, there is the vocab size. There is your residual. I think it's cutting off on the size, right? It is a little slow to move when I'm increasing the font of it. So basically, one thing is missing when you compare it to the transformer architecture. That is your context length. So when you open and try to look at your transformers configuration, you'll get to see a context length there. Here it won't matter because you're just going to keep the latest token into consideration, right? You're not keeping the whole sequence. So this is your config. Then this is basically the picture that I was showing you, right? You have a convolution layer, then you have a silu, then you have X, which is linear, and the linear layer that I was showing you there. And finally, there is always an RMS norm. I think this is very, very, very standard for all the LLMs as well. In Mistral also, you'll get to see an RMS norm when we start. So this is how the model actually looks like. I tried a few very basic prompts. I've used the Slim Pajama model here, just asking what planets are there in the solar system. So let's see. Yeah, the answer, you see, it blabbers a lot after that because it is not a chat-tuned model. It talks a lot about it. Again, I've asked it to retrieve a passkey. So I have uploaded a text file like this, and then there is a passkey in the text file. And I prompted it to respond with the passkey contained in the below text. So it has responded with the passkey, but then again, it has blabbered a lot. So this is happening because this is not a chat-tuned model, but there is another version of the model which is called Open Hermes. This is a chat-tuned model. And this one is a lot more precise in answering your questions. I have asked it to create a Fibonacci series, write a piece of Python code to add the first 5 Fibonacci numbers. So it has given me the code and has not blabbered after it. I've also run it in this part just to see if it is making sense. So basically, you can work with this. You can try to, just a minute, I'll come back. So you can play around with this example. I have also tried to fine tune the model, but that notebook is not here. I'll try to upload that as well in the repo that I have. So these two are the models that you're asking about. Open Hermes is the chat tuned one, and you have simple Slim Pajamas.
Can you share this link on the chat here for audience to try the code if they want to try?
Sure. It is anyhow there in the beginning of the slide deck that I have shared. So anyhow,
you can put it in messaging here, yeah.
Yes, so that was pretty much all that I had for today. If you have questions, you can reach out to me over LinkedIn, or I do have a Medium page as well. I write articles there. You can go through them as well. And if you have questions, you can ask right now as well.
Poulami, there may be some students here. So what do you advise students for, you have significant expertise in this major. So how do you learn? What is your advice for students? They are doing this hackathon, or how are folks supposed to learn and gain this level of expertise?
I think the main component is going to be you're going to be have to very curious. So unless you're curious, you will not be able to explore the different models and the ecosystem that is right now for LLMs. It is extremely dynamic. So every day something new is coming up. And what I would advise is to start with, be very thorough with the basics, be very thorough with Python first. And then next step would be to learn all the steps of the architecture. Start with very basic, starts with RNN, LSTM, GRU, move on to transformers. Then I'm sure Vivek and Cellstrat, they're conducting this regular webinars, and they have this great course which is going on. You can attend those are great. So just build up the basics and then keep on being curious.
So Poulami, before reaching to Gen AI upskilling, MLDL is still relevant, right? We still have the baseline algorithms of machine learning, deep learning are still applicable. And then we go to Gen AI, right? Or do we have to have a stopgap learning in between for computer vision and NLP? Or MLDL, after that, directly we can go to Gen AI learning?
No, I believe that it is essential to have that in-between layer of, if not your images and those things, you have to do NLP in between. So NLP is the basic. If you think about it, all those algorithms, if you think about TF-IDF, that is the basic. That is where it all started from. So those are the stepping stones. You have to be very clear. And you know what, being in my role, I take a lot of interviews every day, and from what I've seen, people are not really aware about a lot of basic statistics. So let's say these LLM and natural language processing, everything, these are very fancy. If you put them on your CVs for the students especially, those will get filtered, right? Those will get shortlisted. But then in the real interviews, there will be questions. Expect questions on basic statistics, things like ANOVA, for example, right? Distributions, very basic stuff. So if you don't know those, then it just diminishes your whole impact on the interviewer, and you don't go in, like, you don't go ahead after that.
It's a good step. So what do you do, Poulami? What is your current role?
I work as a lead data scientist in a company called Cardinal Health. And right now we are building LLM solutions, mostly in the healthcare domain, and also in the customer service as well. So, there are many use cases in the customer service. They are very interesting. So that is my current role.
Great. Yeah, Cardinal Health is a US multinational company, I know, in healthcare space. So
Yes.
that's great. I was checking your LinkedIn. You have been a data scientist in many companies. And so you are advising that start with machine learning, deep learning, statistical concepts, then natural language processing, followed by a Gen AI upskilling, correct?
Correct, yes. No, start with Python before that. Python. Yes,
indeed. So that was great, very interesting new architecture. And let's see if these big tech companies like OpenAI and Google adopt Mamba as a potential choice for LLMs. Audience, any questions for Poulami?
I think at the Sagar, we actually have this, the curriculum is based on what Poulami just suggested, and what the discussion was about. These students are also part of these meetups, Vivek sir, and they have been gaining for some time now from such sessions, and today was a wonderful session. Thank you so much, Poulami.
Thank you.
Thank you.
Thanks
man.
everyone for attending. Yeah.
Thank you all for joining. Thanks a lot, Poulami. Excellent.
Thank you so much, Poulami.